Welcome to that of the UG students for the JAM question solution 2025. Now we are going to that of the first question, the molecular structures of table sugar. The table sugar can be represented by the two structures. One is the sucrose, another is the two structure means it is the disaccharide of glucose and the fructose. And this is the unit of the glucose and this is the unit of the fructose. And these two units can be joined by the anomeric OH group. And it can be represented by the Howard representation formula where the hydroxyl group undergoes intramolecular cyclization to give the pyranose structure. And this pyranose structure after even number of exchange give the alpha D-glucopyranose or the beta D-glucopyranose. Here, the represented structure, the alpha OH group is the bottom side. This molecule is converted to this. Here, the right functional group is in the bottom side, and the left functional group is converted to that of the upside. And this is the alpha D-glucopyranose. And when this alpha D-glucopyranose, after the OH group interchange, this OH group come to that of the bottom side, upside, and we get the beta D-glucopyranose. And in the case of the fructose, after the intramolecular cyclization and the even number of exchange, this compound is converted to that of the formula alpha D-fructofuranose. Here the CH2 is a 2-hydroxymethyl group present in the upside. And when this anomeric OH group is changes, and then the hydroxymethyl group go to that of the bottom side and the hydroxyl group go to the upside. And we know that the structure of the stable sugar is the combination of alpha D-glucopyranose and the beta D-fructofuranose. And hence alpha D-glucopyranose and the beta D-glucopyranose combine to give the structure of the table sugar. And hence the option 1 is the correct. And the remembering point is that the 2-hydroxyl methyl group, the D-fructose unit present in the opposite side in the structure of table sugar. Next is the product formed when R2-bromo propanoic acid is treated with low concentration of hydroxide ion. We know that in the R2-bromo propanoic acid has different reaction in the presence of the OH minus. In the concentrated condition, the SN2 reaction will take place. That is the inversion configuration. That is the OH minus attack to the back side of the leaving group to give the R configuration to the S configuration alcohol. But in case of the low concentration of OH minus, the OH minus is attacked to that of the intramolecular via the NGP reaction. Here, the carboxylate anion is formed, and this carboxylate anion undergoes intramolecular cyclization to give the cyclic ester, and then this cyclic ester undergoes cleavages to give the R2-hydroxypropanoic acid. And after the bromine cleavage, the carbocation intermediate is not formed, as the carbocation intermediate is highly unstable by the carboxyl group. So the racemic mixture of alcohol product is discarded from this reaction condition. Hence, the low concentration of OH minus, it always gives the NGP reaction, and the option predominantly R configuration option is the correct option. The additional problem is taken from that of the from a book where the hydroxyl group THCl means tosyl chloride, can added with the hydroxyl group without disturbing the configuration of the chiral center. We converted the OH to OTS, and then the OH group is more leaving group, and hence it undergoes cleavages to give the ether molecule via the SN2 mechanism, and here the specific rotation value has been changes from that of the alpha to alpha plus specific rotation to the minus specific rotation. Here another condition is that the potassium can react with that of the hydroxide and the anion is formed, and then this anion, alkoxide anion, react with the ethyl bromide with the same configuration. This is called retention of configuration, means the plus specific rotation is same as the plus, and here the plus specific rotation is converted to minus. And this is the main interesting problem taken from that of the J.D. March book. Next is the problem homogeneous catalyst. What is the homogeneous catalyst? We know that the homogeneous catalyst is the catalyst where the substrate and the catalyst present in the same medium, that is the homogeneous. And Wilkinson catalyst is the example of the homogeneous catalyst. And this can be represented by triphenyl phosphine rhodium chloride, where this compound is present in the square planar form. When it added with that of the hydrogen molecule, then square planar form is converted to that of the octahedral form, and then it attacks to that of the alkene, and we get the hydrogenation product. And here the two type of the alkene is present. One is the monosubstituted alkene, another is the tri-substituted alkene. And the Wilkinson catalyst prefer for the reduction with the less substituted alkene compared to that of the more substituted alkene. Again, there is the two alkene, but one is the electron deficient alkene, another is the electron rich alkene. Here the electron rich alkene is participated for the hydrogenation reaction compared to that of the electron deficient alkene. And this is the example of the homogeneous catalyst, that is the Wilkinson catalyst, and this problem has been taken from that of the Carruthers book. Next problem is that of the rearrangement problem, and this is the reaction condition where the potassium cyanide methanol in the presence of the aldehyde benzoin condensation takes place. And the mechanism for the benzoin condensation is that the cyanide minus is added with the aldehyde to give the cyanohydrin derivative, and then this cyanohydrin derivative react with the Cn minus to give the carboanion, and then this carboanion is added with that of the aldehyde, and after the elimination of the cyanide minus, it gives the keto-hydroxymethyl group, and then this keto-hydroxyl group, react with that of the concentrated nitric acid, we get the diketo compound, and then this diketo compound react with the OH minus to give the benzylic acid rearrangement, and we get the desired product. So the option A is the correct. Another additional problem taken from the Credon group, where the pinacol-pinacolone rearrangement takes place via the cleavage of the sigma bond. Here the two four-member ring is joined by the sigma bond by the presence of the cis hydroxyl substituent, and then after the elimination of the water molecule and the cleavage of the sigma bond, we get the cyclopentanone, and then the cyclopentanone undergoes reduction followed by Wagner-Meruin rearrangement. Here the hydroxyl group is protonated and eliminated to give the carbocation intermediate, and then this carbocation intermediate undergoes rearrangement by the cleavage of the CC sigma bond to give the cyclopentane ring with the two cyclopentane fused ring. Next is the problem is an organic compound P C8H16 produce a meso compound upon oxidation with osmium tetroxide NMO. NMO means N-methyl morpholine N oxide. Osmium tetroxide used for the cis hydroxylation. In the given problem, E4-octene is the symmetrical octene. Here the 4 here the three group three carbon containing group, that is the C3 propyl group, and this is the normal propyl group, and they are present in the trans orientation. And after the cis hydroxylation, we get the optically active compound, and this is the optically active compound. And after, if we converted the flying wedge formula to the Fischer projection, then this N propyl group is come to the right side as it is above direction, and the bend is present in the right side. Here the bend is present in the right side, so the N propyl group come to the right side. And again, the hydrogen group is also present in the above direction, and in this hydrogen group come to the also in the right side. So if we convert the Fischer projection formula to that of the flying wedge to Fischer projection, then the trio compound is obtained, and this is the optically active. Z4-octene, after the cis hydroxylation, the two N propyl group come in the same direction. Here the two propyl group is in the same direction, and after Fischer projection, it also comes to that of the same direction. So it is the meso compound, that is the erythro compound, and there is sigma is present, so it is erythro compound. Here the two terminal is not same, so there is no chance to that of the meso compound to get the meso compound. There one is the ethyl group, another the N-ethyl group, so it is also active. Similarly, E3-octene also gives the active. So the option D is the correct. This is a very interesting problem, and this problem came in the NET examination, and this is the very interesting, and stereoselectivity has been changed in the presence of the hydroxyl group by the two conditions. One is the only osmium tetroxide and NMO is used, then the cis hydroxyl product is also formed, but the hydroxyl group is attached in the opposite face of the OH group, means the stereochemical evidence is taken. Here the less hindered hydroxyl group osmium tetroxide is attacked from the less hindered side, and we get the cis hydroxyl product, and the OH group is in the above side. But in the presence of the TMEDA, tetramethyl ethylene diamine, one is the ligand, then it coordinated with that of the oxo group of the osmium tetroxide, and get a chance for the intramolecular hydrogen bonding effect, and hence we get the product where the all hydroxyl group is in the cis orientation. So the osmium tetroxide, in the presence of the NMO, we get the product, that is the 75 is the measure, but in the absorption condition using osmium tetroxide catalyst, the 76 as the measured product. This is a very interesting problem. You can see that. Next problem is the fragmentation problem. The product in the following reaction is for R. Here the carbonyl group is added here, and the carbonyl group can add to that of the Cn minus by nucleophilic addition, and in the presence of the lithium aluminum hydride, the cyanide reduced to give the CH2 NH2, and then the CH2 NH2 has the hydroxyl group, so semi-pinacol rearrangement take place, and here two isomer is formed. Either cyanide group come from the bottom side, or the cyanide group come from the top side. If the cyanide group come from the top side, then the CH2 NH2 group go to the top side, and after the semi-pinacol rearrangement, we get the one isomeric product, and if the another isomer after the semi-pinacol rearrangement, we get the another isomer. So this is the MSQ type problem. So the option C and D are correct. This fragmentation type problem has been taken from that of the Clayton group, where the sodium borohydride undergoes reduction to give the OMS, and the hydride group is attacked from that of the bottom side, and the OMS group in the top side, and after the fragmentation type of the rearrangement, we get this product. Next problem is the state in which all compound yield achiral compound product upon treatment with methyl magnesium bromide ether followed by hydrolysis or with diaryl mineral acid. Here the first option is that the 3,4-ethoxy cyclohexane, after the nucleophilic addition we get the active compound, but the CH3 MgBr we get after the nucleophilic addition we get the optically inactive. That is the two. This is the achiral center. Here the two substitution is the same. So this is not the chiral, this is the achiral, and here also the methyl and this is methyl. So this is not chiral. So this is the optically. So this all set is not produces the optically inactive compound. Next is the ethyl propylate treated with the methyl magnesium halide to give that of the ketone, but here also the acid chloride with the ketone. These are has no chiral center, so it is optically inactive. It is also optically inactive, and this is also optically inactive. So the option B is also correct. And the third option is that the butanone also gives the achiral compound, that methyl, and this is the also achiral center, and this is also achiral. Here no chiral center is present. Here the two substituting the same. So this is the all product produces optically inactive compound. But here this set, the one product is the optically active. So this is wrong set. So the option B and C are correct. This is the problem of the reagent chemistry. The reaction that will yield cyclic product E2-hexene with CH2I2 in zinc copper. We know that this is a Simon-Smith reaction where the carbene can add with the alkene to give the cyclopropane derivative, and by the following mechanism where the CH2I2 and zinc copper produces the carbene and it is added with the alkene. Next, sodium ethoxide and ethanol. This is the Dargent glyceric ester condensation where the alpha to the ester group produces the negative charge and it undergoes elimination to give the epoxy ester, and this epoxy ester is the very important intermediate to formation of the homologation of CHO group. After hydrolysis it converted to that of the CHO, but the intermediate is the cyclic. Here also the ammonia react with the 1,4-diketone to give imine, and then this imine undergoes intramolecular reaction to give the cyclic pyrrole derivative. And so the option A, B and C are correct, but this option is not correct as the cyclohexane 1,2-diol with sodium iodide cleavage takes place, that this is not produces the any cyclic intermediate, cyclic compound. And this is the Simon-Smith reaction where the stereochemistry has been maintained. Here the zinc and copper, the hydroxyl group can maintain the stereochemistry, and the same to that of cyclopropionation take place, same to that of the hydroxyl phase. And the electron rich site is propionated, that is the electron rich cyclopropionation take place. This is the problem of the nucleic acids. And nucleic acids, we know that in the nucleic acid, the adenine, guanine, cytosine, uracil and thymine is the main purine and pyrimidine bases of the nucleic acids. And this structure, the nucleic acid contain the nucleosides and the nucleotides. In the nucleosides contain the nitrogen base and a sugar unit, ribose sugar unit, and in the nucleotide, nitrogen base, sugar unit, and these with the phosphorus unit. In the within problem, the nucleic acids are linked through phosphodiester bonds. That is, the nucleoside bond are bridged by the phosphodiester. This is the nucleoside type, and this is bridged by the phosphoester. And the B option is the wrong. Here the natural nucleic acid have sulfur containing heterocyclic base. Here the heterocyclic bases where the no sulfur unit is present. So these options are wrong. The isoelectric point of the arginine is higher than the isoleucine. This is the amino acids, and the arginine is the basic amino acid, and isoleucine is the neutral amino acid. So this is the basic amino acid. So it has higher isoelectric point and compared to that of the isoleucine. The molecular weight of the guanine is higher than cytosine. Here this is the structure of guanine, and this is the structure of cytosine. From the molecular formula, it has been shown that the guanine has higher molecular weight than cytosine. And this is the additional problem. This is the structure of the NADP, and this is the nucleotide adenosine dinucleotide phosphate, and this is used for the biological reduction process via the following mechanism, where the carbonyl group can undergo reduction via the hydride shift. This is the NMR problem, where the given structure, here the different type of the protons are present in the structures, but here two methyl group is in the same environment. If we take the sigma plane, that is the mirror plane, this is the alanine structure. If the mirror plane is taken, then the two methyl group is separated by the equivalent direction, and a sigma plane is present. So this two methyl group has the same direction, and it gives the same signal. And this hydrogen, this come here, and the phenyl group, this is the orthoproton, present same oriented to same environment. This is the metaproton, also same environment. This is the paraproton, and we get total 5 signals. And this NMR problem taken from the Clayton group, where the sigma bond is not separated, the HA and HB. It is the sigma bond is not present between the HA and HB. If we take the sigma plane here, the HA and HB not equivalent. So the HA gives one signal and HB gives another signal. Here HA is same side with that of the HX, but HB is opposite side with the HX. So the environment of HA is not the same with the environment of HB, and HB present here and HA present here as a doublet and doublet. Next, these black protons, that is the ethyl group, present here and here. So this compound have 1, 2, 3, 4, 5 signal, and this is the diastrobic proton giving the different signal. And this is the numerical problem from the NMR spectroscopy, where the resonant frequency of 1H nucleus is 300 MHz in NMR spectrometer. If the spectrometer is operated in 12 T, means 12 Tesla magnetic field, the resonant frequency of the 1H nucleus. That is the mathematical formula, where the gyromagnetic ratio of the nucleus and the magnetic moment of the nucleus is related by the Lamor frequency, that is the frictional frequency, by the following relation. And if we put that this Lamor frequency is converted to that of the Tesla unit, and it will come to that of the 7.05 Tesla, and 7.05 Tesla gives the proton 300 MHz, the given problem. If it is run in the 12 T MHz, Tesla megahertz, then we get the proton resonate in megahertz 510 MHz. And this is the problem of the stereochemistry, where the number of stereoisomers are possible in the compound. And here the two hydroxyl group either present in the top side, or in the present in the bottom side, or in the present in the top and the bottom side. And here the sigma plane is present in the both of three compounds, among three compounds. So 3 optically inactive isomers are present. And this biochemistry also taken from the Clayton group, where the epoxy compound is not superimposable with one another by their isomer, but this compound is also superimposable with this, and this trans compound is superimposable with this trans compound. They are homomer, and this is also superimposable of this. So they are homomer, but they are enantiomer and they are enantiomer. So this here this cycloepoxy compound gives the 4 isomer that are optically active. Thank you for the watching of the